So our third talk is about motivating effort with information about future rewards. Chang is going to give the talk.
Hi, can everyone hear me?
Yes.
Online, we can hear you.
Okay, thank you. Hi, my name is Chang. I'm currently a PhD student at Harvard, and I would like to tell you about my paper, Motivating Effort with Information About Future Rewards. So the setting I'm considering is a principal-agent problem without transfers. An agent works on a task for a principal, needs to exert effort continuously, and can shirk at any time. The principal would like to induce the agent to work. However, monetary transfers are either prohibited or not allowed, so the principal provides information about the future rewards the agent is going to get from success. As a concrete example, think about the relationship between a principal investigator and a postdoc in a research lab. So typically, the salaries of a postdoc is not directly dependent on the tasks and projects that he is working on, but he does obtain personal credits from completing major breakthroughs. And also, as a predecessor who has worked longer in academia, often the PI knows more about how much reward a particular success will bring to the postdoc. Therefore, the PI can use this piece of information to sort of induce the postdoc to exert effort. And the main theoretical question that I'm considering is how should the principal reveal information to motivate agents' effort? There are actually a lot that the principal can do. For example, the principal can provide an initial disclosure and keep silent afterwards. Alternatively, the principal can delay all disclosures to a certain date and then somehow disclose. The principal can also adopt some more complicated strategies, such as gradually provide small amounts of disclosure in overtime. So in the paper, I sort of categorize the optimal information policy or disclosure rule in close form and identify two key features that make dynamic disclosure valuable. The first feature is that the principal is impatient compared with the agent. And the second feature is that the agent becomes pessimistic over time without any information disclosure. In a stationary environment where the second channel is completely shut down, the answer depends crucially on who is more patient. The principal benefits from any form of dynamic disclosure if and only if she is impatient. Moreover, if she is indeed impatient, then maximum delayed disclosure is optimal. The principal would prefer to delay all disclosures up to the maximum time threshold and then fully disclose. In contrast, in non-stationary environments, the analysis will boil down to two cases. In the first case, which I call no news is good news, the results from the stationary environment will directly apply. In another environment where no news is bad news, the principal always benefits from dynamic disclosure, but the structure of the optimal information policy still depends on who is more patient. Without further ado, let me jump into the model. An agent works for a principal, exerts effort continuously until he chooses to shirk. A crucial assumption is that shirking is irreversible. The agent exerts effort at flow cost C, earns reward Q if he completes the task, and discounts at rate R. I will refer to Q as the quality of the task. In a baseline model of the paper, task quality can take only two values, high or low, but this can be generalized to any number of quality values in the appendix section of the paper. Now, the realized quality Q is the principal's private information, and the agent begins with some prior probability mu that the task quality is high. Both players are going to observe when a task is complete, and completion arrives with some Poisson rate lambda q, which could depend on the task quality. In other words, conditional on the task quality, the duration of the task is exponentially distributed with mean 1 over lambda q. Finally, to close the model, I will assume that the principal receives a bonus b of q at task completion and discounts at some rate rp, which may or may not be equal to the agent's discount rate r. This embeds several cases. For instance, it's possible that the principal's bonus does not depend on the task quality, meaning that b of q is a constant. Alternatively, the principal and the agent may share same or different views about the task, with the difference is that the principal does not pay the direct cost from working on the task. Since my time is limited, I will be brief on the related literature. I will just talk about the most similar one to my paper, which is Illy and Zilovsky 2020, Moving the Goalposts. In their paper, asymmetric information is about the duration of the task, where the principal strategically withholds this piece of information to keep the agent working, even though she knows that the task is complete. In my paper, however, both parties know when a task is complete, so it is impossible for the principal to retain the agent past project completion, and therefore the two papers identify different disclosure policies as optimal ones. Let me define a few payoff functions that will be useful for later analysis. First, I will denote by V of Q the agent's expected payoff from completing a task with quality Q. This is calculated from this conditional expectation, which turns out to have this simple form with a clear interpretation. The denominator R plus lambda Q is the agent effective discount rate from the model. The numerator contains two terms. The first term, lambda Q times Q, is the effective reward, and the second term is the cost. I will assume that the low-quality task is not individually rational for the agent to make the problem interesting. The agent may also plan to shirk at some date tau if the task is still incomplete. If he does so, his expected payoff will be V of tau and Q, which is equal to V of Q multiplied by 1 minus this exponential term. When tau is 0, meaning that the agent shirks immediately, his expected payoff is 0. When tau approaches infinity, this value approaches V of Q, meaning that he gets the value when he chooses to always complete the task. Similarly, I will denote by W the principal's expected payoff when the agent chooses to shirk at tau. Now let me talk about information policies. In the game, the principal observes task quality and chooses how and when to disclose information to the agent. The principal is allowed to make any number of arbitrary disclosures throughout the procedure. And the crucial assumption that I'm gonna make is the commitment assumption, which is that the principal can commit to a disclosure rule. The agent knows the rule and understands the principal's commitment. Under this very strong assumption, it is without loss to restrict attention to a class of signals that produces recommended action, which is an analog to the revelation principle. So the formal definition of an information policy consists of a signal process, sigma t, which informs the agent whether to continue or shirk probabilistically at any time. When sigma t is equal to 1, the agent is told to continue, and when it is 0, the agent is told to shirk. To understand the results, let us start with the stationary case, which I will try to go into full detail. By stationary, I mean the completion rate does not depend on the quality of the task. In this case, the mere passage of time is not informative about the quality of the task. The main results for the stationary case is the principal benefits from dynamic disclosure if and only if she is less patient than the agent. That is, her discount rate RP is greater than R. If RP is indeed greater than R, then maximum delay disclosure is optimal. She will delay all disclosures up to the maximum time threshold and then fully disclose. Let us first look at the static version of the model, which is essentially a special case of Kameneka and Jensko. where the principal provides one disclosure, then the agent chooses how long to work. Specifically, there exists a smallest belief at which the agent begins working, which I call mu bar. If the agent is led to believe that the task has high quality with at least this probability mu bar, he will optimally choose to complete the task. Note that the agent will not have incentive to shirk halfway through because the problem is stationary. Any more pessimistic belief will induce the agent to shirk immediately, and therefore it's familiar that the optimal static information policy, KG, will target at this belief mu bar. The agent will be told to continue whenever the task has high quality and also with positive probability when the task has low quality, just enough such that the agent's belief is exactly mu bar after receiving this optimistic message. Now let's think about the question, can dynamic information policies do better than static ones? Let us start from the simplest possible form of dynamic disclosure policies, which is that the principal delays all disclosures until some future date t, and then fully disclose the task quality, which I call DD of t. At time t, the agent will shirk on hearing that the task has low quality and continue otherwise. And for agent that is sufficiently optimistic at the start, this will incentivize the agent to start working. And the question is, does DDT enable the principal to increase payoff relative to KG, at least for some priors? The answer actually depends crucially on patience. That is the relationship between RP and R, the discount rates. The gain from using DD of t is that the agent always starts working until this time t, regardless of whether the task has high or low quality. However, the loss from DD of t is that the agent might not complete the low quality task, even if he chooses to start working. Since the gain part occurs earlier than the loss part, we might expect that an impatient principal benefits. And this is rigorously established by this lemma 1, saying that for any time t bigger than 0, DD of t increases the principal's payoff relative to KG, at least for some range of priors, if and only if the principal is less patient. And in fact, if the principal is weakly more patient, then the statically optimal policy, KG, turns out to be optimal among all dynamic policies even. Now let's suppose that RP is indeed greater than R, so that DDT is better than KG, at least for some priors. We can actually slightly augment DD of t by allowing the time of disclosure, t, to directly depend on the agent's prior mu. I will denote by t tilde the maximum disclosure time, meaning that the latest time of disclosure subject to the constraint that the agent's ex ante payoff is at least 0. A maximum delayed disclosure simply tells the agent nothing prior to the date t tilde and fully discloses the task quality at this time, t tilde. This will turn out to be optimal among all policies whenever RP is greater than R. So now we are ready to state the main proposition for the stationary case, where when RP is weakly smaller than R, then KG is optimal. When RP is greater than R, then MDD is optimal. I would like to explain a few intuition behind this result. Note that any information policy will induce a lottery over the agent's shirk time. And the principal's maximization problem is essentially choosing an optimal time lottery that minimizes the loss when the agent shirks early from the task, subject to a series of obedience constraints. Under exponential discounting, however, when we apply Jensen's inequality to the principal's and agent's value functions, which contains this 1 minus exponential term, the principal will turn out to be risk-averse over such time lotteries, and the agent will be risk-seeking. And their risk attitude is parameterized by this discount rate due to exponential discounting. Therefore, when RP is smaller than R, meaning that the agent has a stronger risk attitude, the optimal lottery will have a very high risk. It will support on only 2 points, tau equals 0 and tau equals infinity, meaning that the agent either shirks immediately or starts working and complete the task. Note that this lottery will be induced by the static optimal policy, KG. On the other hand, if RP is indeed greater than R, then the optimal lottery will have a very low risk. In fact, it will have the minimum risk. It's degenerate at some future date t tilde. Again, this lottery will be induced by MDD. For the sake of time, I won't go into the full detail of the optimistic and the pessimistic case. I just want to highlight that whenever lambda h is smaller than lambda l, the high quality task will have a longer expected duration than the low quality task, meaning that as the agent starts working and the time goes by, no news is a good news for him because it's more likely that the task has high quality. And the results from the stationary case will directly apply. On the other hand, when we are in the pessimistic case where no news is bad news, it is always optimal for the principal to try to adopt some form of dynamic disclosure policy. However, the structure still depends on whether the principal is more or less patient than the agent. When the principal is more patient, then the optimal information policy now involves a part of Poisson disclosure at some rate lambda h minus lambda l, just enough to balance the downward belief drift by the agent. When RP is greater than R, then MDD remains to be optimal among all dynamic information policies. So I will briefly conclude here. Broadly speaking, I've studied a model of principal-agent problem without transfers and identifies two key features that make dynamic disclosure valuable. First, if the principal is impatient. Second, if the agent becomes pessimistic over time. In the paper, I also consider two extensions where the first extension is the task quality can take more than two values. And another extension is a framework that allows transfers where I define an information wage contract where the principal can choose to incentivize the agent and show that as long as the wage cannot directly depend on effort, most of the insights of the information design part still applies. Thanks.
Thanks, Chang, for the nice talk. So let's see, we probably have time for one or two questions. Let's see whether there are online questions here.
No, I don't see anything here right now.
Okay, thanks, Omer. Okay, let's maybe thank the speaker and next speaker, please prepare for the talk. Thanks, Chang.